Hi, everyone. This week we're talking about Chapter 6 in the Understanding Deep Learning book. So, uh, this chapter is primarily focused on gradient descent and things related to that. I think most people have probably heard of gradient descent, so we'll try and really focus on some of the understanding pieces that maybe are more interesting as opposed to just like the bare mechanics. So far in the book, what we've done is we've looked at a few different models, a simple linear regression, we had a shallow or deep neural networks, and what we're thinking of these as basically you take inputs, you have this function defined by this model, and it has outputs. In the simplest form, right, it has a single output, just like regression or classification. And so we have these parameters, and by changing the parameters, we can have the function output look different. So the question is, now that we have talked about a loss function last week, what we want to do is we want to find the parameters that will lower our loss function. And ideally, we want to find the actual global minimum. All right. So when we find the parameters that minimize the loss, that means that the predictions of our model will be the closest they can be to um, the actual labels. So this is supervised learning. All right. So we've sort of seen this slide before, right? We have a loss function we'll call big L, and we're looking for parameters in this case called phi, and we want to know what are the best set of parameters. So how are we going to do that? So um, here's an example. I can't remember if we saw this last week, but so simple one-dimensional linear regression. Okay, so you have a single scalar input x, you have a single scalar output y, and you're basically going to find a line that's close to all of your data points. So squared loss looks like uh, this over here on the right, right? So the prediction is um, our network is function f, so our prediction, right? We input the value x, and we have our parameters, and we subtract from that what the actual label is, the value y. Um, and so for squared error, what we do is we take this difference, we square it. And we're going to sum this up over all the different examples in our training set, 1 through capital I. So if our linear regression function, f, is basically some constant, phi 0, plus some slope, phi 1 times xi, then you can replace f with this. All right. So this is the function for our prediction minus the actual value squared. And this is what we're trying to do. So the author has some slides where we go through this. And so you can randomly say, this was our starting point, this point 0 over here on the left. And this is a visualization of what the loss function looks like. In the real world, you don't get a pretty visualization, but because this is a small problem, we can actually visualize we have two parameters, our intercept on the x-axis and our slope on the y-axis. This is where we start, and this is what this line actually looks like, this uh, light blue-green line. So we calculate our loss by basically, again, summing the squared differences of the predictions with all of these points. And then we need to say, okay, we want to reduce this loss. So if we do so, then basically um, uh, we can see that moving in this direction, this arrow here will lower it, and you basically get this slightly darker line here. And if we keep repeating, okay, then we'll get better and better lines. And finally, this very dark line is where our loss is the lowest. So again, based on the definition of our loss function, this is the best line. Now, you could have other definitions of a loss function, okay, but with ours. So this technique, as most of you are probably familiar, is known as gradient descent. And so what we're going to talk about is just a little bit more of the background, a little more formalism around this technique. So to back things up a little bit simpler, here's a parabola, y equals x squared minus 4x plus 5. All right. Those of you who took calculus, you can know that there's a closed form formula for the derivative of this function dy dx. And that closed form is 2x minus 4. So when x equals 0, the slope of this parabola will be -4. When x equals 1, the slope will be -2. When x equals 2, the slope will be 0. When x equals 3, the slope will be 2, and so on and so forth. And so what we have on here, as if I advance through the slides, is you'll see at the point 2, we have a slope of 0, so we're going to draw a 0 vector, which looks like nothing. But at x equals 3, the slope is 2, so basically what he has is a line showing moving 2 to the right. So if we were to follow this gradient, this slope, we would move 2 to the right. And then you can say, well, what is the value at x equals 4? 6. What is the value at 1? It's -2. What is the value at 0? It's -4. And so these blue arrows indicate how far you would move if you were following the slope, if you were taking a step of size 1 times the slope. Okay. Now, in gradient descent, we usually are looking for the minimum. So in fact, we would walk in the opposite direction of the slope. All right. So since we're trying to find the minimum, if we started at x equals 4, we're not going to walk to the right. We're going to walk to the left. Okay. And then the other thing that we're usually going to do is we're going to take a smaller step. So we're not going to actually do 1 times the slope. We'll do some smaller value like 0.1, 0.01 times the slope, and take small steps until, for this parabola, you can see the minimum is down here. And so we want to wind up at x equals 2. So that's our basic background understanding. This is a nice 1D problem. It obviously has a little more formalism. It gets a little trickier when you're doing this in high dimensionality. Whoops. Okay, so now here's an outline. What we're going to talk about. We're going to talk about the gradient descent algorithm, and we're going to look at a more complex case, this Gabor model that was in the chapter. So the way gradient descent works is you compute the derivative, in this case from calculus. If you're familiar, if you took multivariable calculus, these are partial derivatives of the loss with respect to each of our parameters. So if we have n parameters, n plus 1 parameters, then we're going to have parameters phi 0, phi 1, all the way through phi n. And we can calculate the slope, as it were, the partial derivative of our loss function with respect to every single one of these individual parameters. And if we line them up in a vector, then this vector we can just call the partial derivative of the loss with respect to all the parameters. Okay, where phi here is not a single variable, but this is a whole vector of parameters. And then our update, like I said, is usually you're going to take a small number like 0.1, 0.001 times this slope vector. And you're not going uphill, you're actually going to subtract. You're going to move in the opposite direction of the slope. So you're going to say my parameters are updated by subtracting a small amount. And this alpha, this is, often known as our learning rate. Okay, so we can take this linear regression example that I showed before, and we can actually go through a little bit more rigorously. We have a different starting point. So our starting point now is over here on the upper right. Same equations before. We're doing the sum for every data point in our training set. Training set's not shown here, right? And we just have our prediction minus the actual value squared. So we can actually compute these partial derivatives, not uber important for the purpose of understanding this. But if you do know your calculus, then basically for the bias term, it's going to be 2 times our error. And for the slope term, it's going to be 2 times our input x value times the error. So based on this, you're going to get sort of your on here, we have the intercept as the x-axis. So we'll get a horizontal vector that's of length this first item, and we'll get a vertical one that's this. And if you add them together, we'll get a diagonal. And so that's what we're going to see right here. Okay, is that this is the partial derivative with respect to the intercept. This is the partial derivative with respect to the slope. And if you combine them, then this is the uphill direction, this sort of northwesty direction up to the left. So we are going to go in the opposite direction. We want to go downhill. So then you're going to see this arrow is the reverse of the one we just had, and this is us moving downhill to try to lower our loss. So once we've moved downhill, then we're going to arrive at a new point. We'll call that point 1. Okay, so here's our point 1. And this was our original, this light line was our original 0 line. It's really terrible. And here's our new line for point number 1. I guess it's better, but it's still like pretty significantly terrible. If we repeat the process, calculate the partial derivatives, again, you have your sideways component, your up component, combine them, you get a diagonal line. And again, we're going to go in the opposite direction. So we're going to go southwest down into the left. And so moving in this direction, we get to a point number 2 over here. And then to my eye, I can say, okay, this line 2 is much better than the other one. So in this case, we've changed both the slope and the intercept quite a bit. Repeat. Again, we get 0.3, 0.4, and eventually you can see that this 0.4 isn't necessarily quite dead in the center, but it's near the center, the darkest point with the lowest loss. And then to my eye, this dark line does seem to fit all these circles, these dots, much better than where we started. So if any of you have seen gradient descent, you've probably sort of seen this. This is sort of the high-level concept. And at this point, what we're talking about is full batch gradient descent. So if you go to scikit-learn and you train a linear regression, what happens is you give it all of the data at once, and it does its thing. Okay. Probably most of you know that when we're training our neural networks, we don't do that. Okay, we do mini batches. So we haven't gotten to that yet. This is still talking about the basic theoretical full batch gradient descent, where you go through all your data and you calculate one single gradient, which is the best direction based on the entirety of your training data. The author talks about line search. I don't think that's too important, so we're going to kind of skip over that. All right, and then the next thing is we're going to talk about convexity. But so first, any questions or comments just about like the general algorithm of gradient descent, where basically we pick the direction that's downhill, the steepest downhill, with respect to all of our parameters, and then once we have that, we take a step in that direction with the intent of constantly lowering our loss function. All right, so at this point, there's a question in the chat. We have not said how um, so there's not really an approximation going on here. Basically, what's happening is you take all the data, you make your predictions based on your current parameters, and you see how far off your predictions are from the actual values. From that, you calculate your loss function. Based on that, you will have a very specific numerical loss for each data point, and you will have the derivatives with respect to each parameter for each data point. If you sum them all up, average them all up, you will get a single value for the most downhill direction, the direction in which changing your parameters most quickly lowers your loss function. Does that answer your question?
Yeah, kind of. I think you're getting to it.
Yeah. So at this point, this is not about approximation. This is a deterministic algorithm that if you pick a certain starting point, it'll always do the exact same thing every time. When we talk about convexity, this is now where we get to the issue of, does this algorithm actually do what you want? Okay. Um, and so high level basically, convex basically says that, hey, in the middle, we've got something convex, and it means that, to formal definition, right? If you draw uh, a line segment between any 2 points on this curve, it'll never cross the curve. You'll constantly stay above the curve. Okay. Loosely, what that means is the thing has to be basically bowl shaped. It can't have wiggles like this thing on the left or this thing on the right. Okay. They have wiggles, and that's not allowed. And you can easily see that, for example, if on this example on the right, if I drew a line segment from point 6 to something about here, I'm actually going to cross myself twice. Okay. In this one in the middle, it is impossible to draw a line that crosses uh, the function. So the reason why we care about convexity is because you get this phenomenon of local minima. So 1 and 3, if you only look at a skinny region near it, um, they are the minimum, and there's uh, if you only look nearby, right? There's no better place to be than specifically just at that loss value. So with gradient descent, you can wind up in a local minimum. And in fact, if you have what we'll see in a minute is, you have a complex enough function, nobody knows where the global minimum is. There is no algorithm. It's not just that gradient descent isn't the best algorithm. There is no algorithm in the world that can for sure find you the global minimum. All right. And so this is the big problem we have with these iterative methods, with these approximate methods, is that once you're in a minimum, it's not even like, oh shoot, I'm in a local minimum. No, you don't even know. You know you're in a minimum, and that's all you can know. You have no idea if there's better ones, worse ones, or if there even are any other minimum. Maybe there is only one, but you can't actually know that. So conceptually, we'll talk about a couple things, but let me pause here. Yeah, there's a couple questions. Yeah, raised hand.
So are there sort of, practically speaking, I guess most problems that we'll be dealing with will be sort of non-convex. Are there practical things that are done to find a better local minima in the actual training?
Yeah. So we'll get into a little bit in the rest of the chapter, but the the short answer, the simple answer is there is no real solution to this problem. Okay. What ends up happening in machine learning is that when we build these deep learning models, they actually work really well. Where uh, if you try 10 different initializations, you'll wind up in 10 different local minima, and odds are they will have almost identical performance. So this is there was a little bit in the chat last week, but so this is one of the still unanswered questions about deep learning. Why is it that gradient descent works so well? Why is it that we don't get stuck in bad minima very often? I mean, we don't get stuck in bad minima even 2% of the time, let alone half the time or 3/4 of the time. Uh, so there's a bunch of active research still in that. But practically what it means is that even though we don't think these neural networks are convex, there is something about the 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 shape of the loss and the way we train them that we somehow seem to be finding minima that are really, really good regardless.
Oh, great.
Um,
Thank you for explaining that.
yep, yep. And so this is definitely not true. So if you just go and pick some random problem from physics or whatever, like gradient descent will not necessarily work so great. But for neural networks, it seems to be working really great, which for us is a tremendous boon. All right, there's another raised hand. Yes.
Um, I just wonder if we can check loss function, if it's theoretically even possible to check loss function in every point.
Oh,
Yeah, yeah.
this is a huge amount of computations, which will can take, for years. So we
So
don't do this. Okay.
yeah, yeah. I mean, we have several problems. So even if you had a one-dimensional problem, you would need to know how wiggly it is. Okay. If you have a limit on its curvature, so I don't know, like, we're talking about like, I don't know, Lipschitz constants and things like that, then you would know, like, oh, if I checked every 0.1, that would be good enough to know that if something's going on. But if you don't really know how wiggly it is, if you checked every 0.1, then maybe there's this like really great thing that's like halfway between, 0.05. Suddenly there's a much better, right? But if you said, okay, fine, then I'll check every 0.01, well, then if you don't know how wiggly it is, there could be something in between those 2 points. So that's sort of one problem we have. And then the other is just that our problems get to be very high dimensional and very large. And so then even just checking between, say, the values of 1 and -1 every tenth, so 20 odd points. If you're doing this on, say, uh, something that has a million parameters, now you're talking about whatever 20 to the millionth power, and it already has become completely intractable. That was part of the reason for the line search thing that I skipped, is that there is sort of a method that you can use to try to find good, but it just doesn't scale for high dimensional problems.
Okay, I want to say the following thing. If you subtract all mathematics, then what we are doing with the gradient descent is the following thing. We are on some kind of terrain. In the dark, we cannot see around. We have only small flashlight with which we can lighten up the ground near our feet. And we can determine that there is some slope in some direction. And what we do the next, if we have device with which we can jump. If we choose the direction, if you choose the value of the jump, and we'll end up in another point, and we are in the same conditions. We cannot do anything around. We cannot see anything around. We can look only under our feet to choose the direction of the next jump. That's it. So
No, that's great, Maya. Yeah. So given only this flashlight that you can see really close around you, you're trying to find the lowest point, the lowest bottom of the lowest valley. You could be in a very deep valley and be pretty happy, or you could be in a small crack at the top of a mountain and you would have no idea because your flashlight can only see, a foot in any direction. So that's a good analogy. All right. So we'll throw a little theory in here, okay? So you can actually test for convexity, convexness. I don't know. You can test to see if something is convex, um, because if you know calculus, the first derivative tells you the slope. The second derivative tells you how the slope is changing, okay? And so if your second derivative is positive everywhere, then you're convex. And if you extend this to multiple variables, okay, now instead of talking about the second derivative, you're talking about all of the second partial derivatives. And so we'll get to that in a minute. But so then you basically have your Hessian. Okay, so here is here's the Hessian for we only have two parameters, just phi 0 and phi 1. And so this is a 2 by 2 matrix, okay? If all four of these numbers are positive, then our particular loss function is convex. And again, we're just talking about this theory so people understand, okay? just to be clear, we're not in practice ever going to be doing this test for our neural networks. All right, so that was a nice simple model. It was the linear regression was convex. Now he's going to give us this more complex model just to show us what happens when things aren't convex. So here's this Gabor function, and basically what it looks like is this squiggly thing, okay? It has big squiggles in the middle, and then it fades out to pretty close to a horizontal line. And it has two parameters, again, just like linear regression, phi0, phi1. And based on these, you can either shift the squiggles left and right, or you can either smush them more compactly like B, or spread them out wider like C. Those are the only two things you can do with this function, all right? And so then let's say this is our set of data points here. So there's clearly higher and lower ones, and what we want to do is we want to fit this particular squiggly function to it. And if we were to map a whole bunch of points, then basically what we will see here, this is the loss function, and darker means a lower loss, which is what we want, and lighter means a higher loss, which is what we don't want. So the example shown here, this is the same one that was in the book, is if you look at these various dots, these are each local minima, okay? And so this local minima B corresponds to this point over here. If you have your flashlight, you can only shine in a small circle around here, you will see that it's uphill everywhere from here. But it is not even remotely clear to get out of, even if you suspected you were in a local minima, it's not clear what direction you should go. Should you go to the right? Should you go up? Should you go left? Should you go down? How would you know? And similarly, if you're in this local minimum. Now, because this is a toy example, we actually know that this particular local minimum right here is the best one overall. Okay? But the instructive thing to see is that there's no real way to know just from any other local minimum what direction you would go. And so this is what neural networks, this is what pretty much everything other than a toy problem looks like. And so the whole idea of convexity doesn't really help us. Okay, so ultimately we're going to do gradient descent, but we want gradient descent to work quickly, and ideally we'd like it to not too easily get trapped in local minima. So if there's just like a small little depression, we want it to skip past that. We want it to look for a nice, really, really deep valley. And that's the concept here. So here we show 3 different initialization points, 1, 2, and 3. 1 and 3 happen to go to this minimum, and 2 happens to go to that minimum. And in this case, we know that 1 and 3 are actually getting to the global, but 2 isn't. But that's, again, just because this is a toy problem. Normally, we would have no way of knowing. So when you talk about the mathematical effects of gradient descent, remember, this is, again, full batch gradient descent. We go through all of our data. We calculate what is the steepest direction downhill. So it's a deterministic thing, and you're going to see this behavior where, again, different starting points move to different local minima. And in fact, you see this sort of zigzaggy pattern, which I'm actually not that familiar with because, I mean, honestly, like I've never done full batch gradient descent, right? It's like talk about it in textbooks and then you move on. And so, but with full batch, there's a question at the end of the chapter, and if we have time, I'd like to talk about that. But you see this actual zigzaggy pattern with the gradient descent. So what we're now going to talk about is stochastic gradient descent, which is both more practical and win-win. It's actually tends to do better performance than full gradient descent. So that's a win-win. the idea is in full batch, you have your training data set, which has capital I items, and you calculate loss over all of them. But in stochastic gradient descent, technically mini batch gradient descent, you take some subset of your data, which is your batch here, this little curly B. So maybe this is 16 data points, and you calculate what's the gradient on the 16 data points, and you follow that just like normal. But because this is a subset of your data, it may not match, and probably does not match, the exact gradient that you get from the full. And in fact, it could even be completely in the opposite direction. Just if you happen to get kind of a random set of training examples. So there's a lot of randomness to stochastic gradient descent, to SGD, that doesn't exist in full batch gradient descent, which is 100% deterministic. And it turns out that we like having some of that randomness. So here, you can see that this 0.2, which would have gone to a different local minimum under full batch gradient descent, under SGD, it kind of wanders in the wrong direction a little bit. It goes a little bit south. Okay, you see my mouse, it goes south a little bit, which is not really the direction of steepest downhill. But because of that, it actually winds up eventually going a little bit to the left, going a little west, and it winds up in this, our best local minimum. All right. And the idea is that if you have some randomness, the bigger and deeper the valley, the harder it is for you to get out of it. So, so for this randomness, why it helps you is because if you have a small local minimum that's not so great, then your chances of popping out of it are pretty decent. But if you have a giant, super deep valley, then the odds of you accidentally popping out of it by having a few gradients that are actually uphill in the wrong direction become much, much lower. So the idea then is that the bigger, deeper your valley, the easier it is to get stuck in it. Therefore, SGD will tend to find better, bigger, deeper valleys than just a straight deterministic full batch gradient descent. All right, there's a question in the chat about how does SGD compare with a simulated annealing approach. This chapter doesn't really get into it, but there are further additions that people layer onto SGD. So a very simplistic thing you could do is you could say, I'm just going to train my neural network 10 times, and I'm going to pick the best of those 10 trainings. Okay, that's a very straightforward thing you could do. But it turns out there's other things that you can do. So typical things that you see are you start with a larger learning rate, which increases the randomness and allows you to get out of local minima a lot easier. And so the idea is you want your algorithm taking big jumps at the beginning, just to try and sort of find where there's like a really giant valley. And then ultimately you need to lower the learning rate so that it can actually like walk down into the valley. Because if you have really giant, jumps, then you might actually be jumping out of valleys, right? So like simulated annealing, you basically like lower and lower the temperature, you lower the noise, you lower that learning rate, so that SGD can sort of settle down in there. Another technique that people use is they do cyclic learning rates. So you do something where you start with a very large learning rate, it's jumping around, it's hopefully jumping out of small valleys, possibly getting stuck in a big valley. And then you do some kind of learning rate reduction to find the bottom of that valley. All right, so you say, okay, now I'm in a pretty good spot. Now what I'm going to do is I'm going to raise my learning rate, maybe not to the same initial value, but I'm going to raise it to a high learning rate and repeat this process. And if I just got a little bit unlucky and I'm in not that great of a local minimum, then maybe this will jar me out of it. Okay. If it is a really good one, then I'll either stay stuck in it, or even after I get jarred out of it, I'll just wind up coming right back into it. And so you might repeat this cycle of big learning rate and then slowly lower it a handful of times. I think Jeremy Howard, Fast AI, is a big fan of the cyclic learning rate thing in order to try to really find a good valley. But ultimately, it is still just a little bit of luck, what kind of local minimum you wind up in. And the good news is in machine learning, we somehow seem to be finding good ones. All right. So a couple more diagrams about the Gabor model. I don't think we need to go into too much. And then, yeah, here's the learning rate schedule. I can't remember how many slides we have. No, there's not too much discussion about that. So then the next thing we're going to talk about is momentum. And the idea of momentum, the word momentum was chosen because it's kind of a good intuition. So basically imagine that, you really have a valley, in a mountain range, whatever, but it's bumpy. There's rocks here and there and whatever, and you have a bowling ball and it's just kind of like rolling down. And you're trying to find the bottom of the valley. At any one given point in time where you're on the local surface, the steepest direction downhill might veer a little left, veer a little bit right, but on average, it ought to just be sort of like straight down towards the bottom of the valley, right? And that's, if you have a bowling ball, that's what's going to happen. It's not going to turn left and right super quickly. And so it's going to average the lefts and rights, and it's going to just sort of like, keep going down based on the average of all of those things. And that's what this momentum does, basically, is it says, hey, last time I took a step in this direction, okay, I'm going to have some constant beta, which is between 0 and 1. And so what I'm going to do is, let's say beta is 0.5. Then I'm going to use half my weight on the direction I was going and half my weight on the gradient that I calculate this time. And I'm just going to average those two together and then keep going that way. All right. So instead of just calculating the gradient at exactly your spot and using just that, you do a blend of your current gradient plus your past gradient. So this tends to actually work pretty well. And so if you see on the left, no momentum, you're sort of very detailed following the contours and you're sort of doing zigzaggy. And on the right, you can see momentum. Occasionally, momentum will take you in the wrong direction, but after a few steps on average, the little left and right turns will sort of cancel out and you'll just sort of head much more directly, much more directly towards the bottom of the local minimum. Sorry, my mouse keeps double clicking. There's another concept, the Nesterov accelerated momentum, and I don't think it's super critical that you understand it, but it's kind of a cool concept. So the idea is if you came into point 1 from this dotted line direction, okay, so then this is your current momentum. Typically, what we do is we calculate the local gradient, and so let's say this is the arrow from point 1 to point 2. So like I said, we have some factor beta that says we're going to average our old momentum plus our current direction. And maybe you get something that's kind of like in the direction of 3 or something like that. What Nesterov, what this algorithm says is instead of measuring the gradient at point 1, let's keep going with our momentum a little bit to point 4 and measure what the gradient is there. All right. So essentially what regular momentum does is it says, hey, I'm going to calculate my gradient, but I'm also going to kind of average it over time. And so I'm going to sort of take this blend. What the Nesterov accelerated momentum is doing essentially is it's like the idea of assuming that the momentum is right. Okay. And so instead of saying I'm going to take a little bit of momentum and average it with my current gradient, I'm actually going to assume the momentum was right and keep going in that direction, and then take the gradient from that place further down. So it's a little bit like taking a bigger step in the momentum direction. And empirically, I don't know, some people like Nesterov. I haven't seen anything that says very definitively it consistently beats, doesn't beat. Oftentimes you get just sort of similar answers. All right. And then the final thing to talk about is Adam. Adam's very important. And so if you're not familiar with how Adam works sort of under the hood, the idea of Adam is that you could have a surface that is steeper in one direction and shallower in the other direction. And that can be very tricky for an SGD gradient descent type algorithm. I think this diagram is actually sort of flipped conceptually. But basically, if you did gradient descent with a very large learning rate, and you're taking two big steps, then instead of taking small steps like on the left directly towards the valley, if your steps are too big, you actually overshoot the bottom of the valley and you wind up on the other side. And so this can happen back and forth. And so yes, you can do this by lowering your learning rate, but it gets kind of tricky. What Adam does is it helps you avoid having to worry about that business altogether. So here's this formula. For time's sake, I'm not going to go into it too much, but basically if you measure the magnitude of your gradient direction aside, okay, then this formula will basically normalize it so that you end up with a unit vector, okay? You've taken away the length. You just are now talking about the direction and not really the magnitude of it. So you could do something simple with normalized gradients. And what you're supposed to see in this diagram is that like each one of these steps is the exact same. The directions change, but each one of these steps is the exact same size. This is what happens if you use normalized gradients alone, okay? But Adam is beyond normalized gradients. Adam is, let's do normalized gradients and also have momentum. So not going to kind of, get into the formulas and all that. So we take the concept of momentum, we had normalized gradients, and then we add this other thing, which is, again, not super important to know the math, but basically the thing to understand is that when we get started, we have very few data points. We don't have a lot of history. And so our momentum calculation is kind of crummy. All right. So what we want to do initially is we want to take some slightly smaller steps and downweight these calculations because we don't have a long history. Once you have like a history of like 100, calculations, then you can say, yeah, my average downhill is a pretty good average. But when you only have 5, maybe that's like not very good. All right. So Adam's going to introduce a parameter beta, which we've seen before, which has to do with how much you lean on momentum. And it's going to have this new term gamma, which has to do with moderating things at the beginning, I believe. And so then we now have a comparison. On the left is the one we saw before with just normalized gradients. And now this is Adam. So because it has momentum, then this part at the end before you saw that was just sort of this zigzaggy thing. Now we get sort of a much more smooth, where we can go in different directions, a smooth spiral. Also, if you note, whoops, sorry, my mouse keeps doing that. Regular gradient descent, when it gets to whatever, this middle point here, sort of makes its first hard right turn. When you have momentum, if you have like this bowling ball that's rolling downhill, you can't make a hard right turn. And you'll notice that momentum does actually cause you to overshoot the bottom. So it goes much, much farther up past the bottom of the valley, whereas here, we don't do that. So that's sort of the downside of momentum in terms of like it's going to overshoot the bottom and have to come back. But the upside, why pretty much everyone uses it, is again, you don't want to get stuck in a lousy local minimum. And so That's why pretty much everybody uses momentum. And so Atom works really well. And I think a simple thing to say would be, if you're doing any kind of neural network deep learning, if you don't know better, your starting point should be use Atom as your, what we call an optimizer, but basically as your tweaked gradient descent algorithm. All right. The author mentions that the choice of learning rate, algorithm, or optimizer, your overall learning rate, choices for momentum, things like that. In the chat, talks about what values for beta and epsilon you use. These are all hyperparameters. And even with the exact same architecture, the exact same initialization, you can get different answers by modifying your hyperparameters. All right, so that's the end of the slides. We're pretty much at time, but I wanted to just hit on a couple of the problems at the end of the chapter. So the problems don't really seem to go in order necessarily. So problem 6.8 asks, can regular gradient descent, not stochastic gradient descent, with a fixed learning rate escape a local minimum? So does anybody have a thought about what the answer to 6.8 is? Is it possible to get out of a local minimum with just regular gradient descent, not SGD?
Well,
Yeah.
if we don't have a condition that we should find the local minima, then we can jump around whatever, get a big fixed rate, and we'll escape local minima. It is just we won't find global minima. We are not likely to find it, but well, we can escape it.
Okay. Yep. And there was a hand raised.
Oh, I just wanted to say practically the same, similar thing, that it probably depends of the how big that learning rate is. If it's bigger than local minimum, we can escape it.
Absolutely. That's right. So the important concept here is that SGD people believe on average is better at escaping, but it's not because it's impossible to escape a local minimum. And so, yes, something like simulated annealing, cyclic learning rates might help you even without SGD, but you can always combine the two and have the best of both worlds. So there's this question 6.9. Hey, if you run 1,000 iterations on a data set of size 100 with batch size 20, how many epochs? And early on in deep learning, people talked about epochs quite a bit, but then people realized that, like, well, epochs is just how many times I went through my data, and it really depends on how big my data is. So, for you to say, well, I trained 10 epochs, it really means nothing. If you train 10 epochs on a small data set, then you really didn't do very much training at all. If you did 10 epochs on a 1 billion point data set, then that's a lot more training. So basically, people have moved away from talking about epochs to really just saying, hey, how many data points did you look at? So for large language models, you'll see they say, how many tokens was it trained on? It doesn't really matter how many epochs that was the equivalent of. On the more mathy side, problem 6.11, what dimensions will the Hessian have if the model has 1 million parameters? Okay, so my model has 1 million parameters, phi 0 through 5, 999, 999. And I have a single loss function. Okay, so my big L just outputs one scalar value. All right. The Hessian is defined as like all of the second partial derivatives with respect to each of the different parameters. And so it is going to be an array. So anybody have any thoughts on what the size of that matrix or array is going to be? Anybody here have some good multivariable calculus background? Yeah, it's in the chat. So 1 million by 1 million. And thank you, actually, yes. If it's symmetric, then technically you can divide it by 2 in terms of like unique values, approximately by 2. But so a model with 1 million by 1 million parameters, the Hessian is, so millions 10 to the 6th. The Hessian is going to be 10 to the 12th. So just even to store that, right, as floating point numbers would require like 4 times 10 to the 12th bytes. Okay, so 4,000 gigabytes for a single Hessian. So this is like at one step. All right. So, and these days, 1 million we know is not really that big of a deep learning model at all, right? I think GPT-2 was what, 175 million, and it's considered relatively small by today's standards. Right? Whatever, 2 billion for an LLM is pretty small. 6, 7 billion is sort of the minimum, right? So this is why when we had the conversation about convexity, practically speaking, people are not actually looking to see, as was mentioned in the chat, people are not looking to see like positive definiteness. People are not looking to see, to calculate this Hessian. The other thing is you can use the Hessian to improve the steps that your gradient descent algorithm takes. I'm not a big expert on optimization, but like Newton's method, other techniques, you can use the second derivative in addition to the first derivative, which is the gradient. But you can see why people are not calculating second derivatives, because you would need, again, for this thing, you would need this 10 to the 12th size array just to calculate this set of second derivatives that would help you take one step. And we're often taking millions of steps. So very impractical. All right, I will pause here in terms of the problems that I wanted to go over. But if anybody has looked at the problems and has questions about any of the other ones, then we can kind of dig into that here. All right, so then let me just open it up. Any questions about the overall concepts in this chapter? We have a set of parameters. We're going to try and tweak those parameters in order to lower our loss. So we're going to use gradient descent. We add the concepts of momentum and this normalization that's used in Atom. Yeah, there's a hand raised.
So can we change hyperparameters during calculation of gradient descendants, or it should be like constant until we end the calculation?
Can we change the hyperparameters? So certain hyperparameters are easier to change than others. So like we already talked about, people often change learning rate during training. I don't know if people talk about changing momentum or anything like that. It gets complicated. And then other hyperparameters like your model architecture and stuff, generally speaking, no, once you start training, like those things aren't changed. So I think the overall answer is yes, it's a valid thing to do. You just you have 2 questions in my mind that you answer. So one is it valid? Are you going to break something if you change it? Okay. And so if you change momentum, it's probably not going to break anything. But the second question is, do you know when you should change it?
Yes, this is a question. So is there like some law or some rule how to change, how possibly like, or only from, for example, 0 to 100 and just with some step, or at some point we should change it from 0 to 0.5 step,
Right.
or we should look how gradient descent how it convex, right?
Yeah, so the answer is that there's practical tips that people learn by doing multiple trainings, and you can see this advice, but there really isn't any formalism. So like a very common thing is people use a cosine learning rate schedule. So if your learning rate starts at some value, 10 to the minus 3, then you're going to end at some predetermined point, 10 to the minus 4, 10 to the minus 5, 10 to the minus 6. Usually it's on that scale, right? Either a tenth, a hundredth, or a thousandth of your initial learning rate. And you just follow a cosine curve where it sort of stays flat for a while and then gradually decays down to your final value. But even that, it's sort of like uh, um, it's kind of just sort of like made up that if I had 100 billion tokens to train on, then I would do this decay over 100 billion tokens. But if I had 200, I would do the same thing over 200 instead of 100. And so it is a little bit of just sort of art, not science. And so the bad news is there's no theoretical guarantees. There's really no whatever. But practically speaking, there's a lot of advice out there from people who've done it before saying this is what worked. And also, again, one of the mysteries of deep learning is that we're often talking about the difference between like a 1% difference in the performance of your model. Okay. If you didn't follow the advice, if you didn't use the best learning rate schedule, whatever, then, your thing that can classify, different kinds, different breeds of dogs, maybe would have 94% accuracy instead of 95% accuracy. It's not like it would just completely fail because you didn't follow the best recipe.
Yeah, it depends of what we have to get at the end. What accuracy, right? Yeah, thank you.
Yeah. And so unfortunately, because there is no super direct way to find the best one, what that tends to mean right now is that there's an advantage for the big players. So the big companies have the big money that they can afford to do this training. If you just have a couple GPUs, you cannot afford to train this 10 times to try lots of different things. And so you're kind of stuck with your more limited resources.
Okay, thank you.
Yep.
I just want to note that you can look up at implementations, and sometimes they have something implemented. For example, I know that learning rate scheduler decay, exponential decay, it is implemented. You can
Oh
try.
yeah, it's implemented, but whether or not you should use that one or a different one.
But theoretically, you can always implement it on your own, do your own custom thing. It is just I recommend to look at first at what is up already here.
Yeah, no, absolutely. Yes. Then you're not dealing with bugs, at least in your code. But again, whether you should use that cosine one or that exponential one, or stop on plateau or whatever like that, then yeah, it just gets into a whole bunch of sort of ad hoc conventional wisdom recipes, things like that. Got two hands raised. So Alex first.
So somewhat kind of related question to what Nadia was asking, but do we have a sense of how the architecture that you choose affects the optimization? So for example, I'm thinking of, if you're doing an image classification problem, you pick a convolutional neural network, you wouldn't use a fully connected one. Is that because, the advantage that you get is that you can use less parameters, or does it change the loss landscape somehow? Do we have a sense of this?
I can give you one specific example. The initial convolutional nets, the initial CNNs like AlexNet, did not have residual connections. And ResNets are much easier to train and much faster to train. ResNets were sort of invented because people wanted to build bigger and bigger CNNs, but they ran into problems. As the CNNs got deeper, they really ran into issues. people have visualized the loss landscape for residual and non-residual CNNs, and you can see that the residual ones, it is a much smoother, much less bumpy surface, and it's much easier for these algorithms to just find the right direction to go downhill. Because at any point in time, you're predominantly pointing downhill, whereas if it's this incredibly bumpy thing, you just have this local surface that basically can point you in any direction, right? So so I know that that's like one concrete example, and there's so just in general, like you'll notice that everything these days is a residual network. So transformers are residual, Mambas residual, everything, you know. So there are things that people do like that, but otherwise, like I don't know if people would say like the difference between I don't even know if I can come up with a good example, but like, you know, a dense layer versus a CNN layer. I don't know if there's anything like that that says that, you know, one, whatever. There's other reasons why like CNNs work better than fully connected in terms of like there's inductive bias and things. And so if you have the right inductive bias, then training will be faster because you are essentially forcing the model to ignore noise in things that you just, you know, so in the CNN, it can't see pixels far away, and you're forcing it to ignore any spurious correlation with pixels that are not nearby. And that turns out to be a very good thing for images. But for more complex problems, as the problems get more complex, so like for language, we no longer have a good inductive bias, right? People tried things like, oh, can I do part of speech? Can I do grammars, whatever? But ultimately, we didn't have any powerful inductive biases. So we had to use a generic model that could learn its own inductive biases.
Right, that makes sense. Thank you.
Yeah, thanks for the question. Yeah.
Yeah, I want to state, maybe it's obvious, but I want to state it just to make it complete, the whole thing. So as the number of feature increases, the number of observations you need, and then also the iterations. So let's say the iterations you need to execute will also increase. This is very obvious, but I wanted to mention that one thing. Another thing, like, so when do you know when you need to stop, when you learn the parameters? That's also the stopping criteria is important, critical thing, right? And then for that, people use like non-improving iterations, or some people use basic the number of iterations. But yeah, I wanted to mention these two obvious things just to complete the whole thing.
That's really great. Yeah. And so based on your first point, if you have a deep network with a lot of parameters and that requires more data, that means that this is not an appropriate model for a problem where you don't have a lot of data. So if you say, I work for the power company and I want to detect certain problems with, you know, my telephone poles. If you say I have 500 images, you can't use a deep network for this problem because of what you said. It's going to require a lot more data to get it trained accurately.
Even if you have a lot of images, if you still need a lot of iterations to be able to train those parameters. You need to have first thing, you need to have this tall matrix. You know, your features must be less than your observations. Also, you have significant amount of iterations based on the parameters you're tuning.
Right.
Thank you.
Yeah. But I'm adding on to what you're saying. So like, so you get hired by a company, you're a new data scientist, and it's a startup, and they say, yeah, we hit a milestone. We have our 1,000th customer. We just signed up, and we're growing very quickly. And I want you to build a customer churn model. And they say, so we have 1,000 customers, and we've lost 50 customers. You can't use a deep learning model on that data. You just don't have enough data for that problem. So it's a really, really good point. And so we're learning about this, and yes, I don't think the author has said it, but I'm glad you brought it up. You do need to ultimately decide when is it appropriate to use deep learning? And if you have enough data, there's a decent chance that as long as you don't need explainability, the deep learning model will outperform other things that you could use. But if you don't have enough data and you don't have the compute time to run it, then you're dead in the water. It's a really good point.
You might need to change your model, go with simpler parsimony models.
Yeah.
And also the
Thanks.
substance criteria, that's also very critical.
Mm-hmm. Yes, yes. And then eventually when we get to LLMs, we'll find that there's this other phenomenon that people initially were training them to the best performance. But then there's this phenomenon that since the compute's so expensive that it might be that a different model that you trained the same amount, it didn't get to that model's best performance, but it still beat your performance. And so if you're familiar with the chinchilla paper, that really is when people started focusing on compute optimal versus for a given model, train it till it gets its absolute best performance, which might require a lot more compute.
Yep, thank you.
Awesome. All right, we're over time. Thanks for staying an extra 15 minutes for those of you who could afford to. I think we'll stop the recording here.